Hello, Chem 2. Welcome to another edition of Thermochemistry. Hopefully everybody is being safe and healthy. Everything's going well. I know we've been away from one another for approximately 4 weeks now. And I know this has been really, really crazy. So today what we're going to talk about is next two pieces of the sections, talking about rules of thermochemistry. And you'll see where those apply. It's basically what happens in regard to enthalpy and what that's all about. And then we're going to apply what's called Hess's law, a way to calculate this change in enthalpy. Delta H is a change in enthalpy. So administrative items, 1, chapter 5 exam, you got that on your plate. Should have finished it by Tuesday noon. Hopefully that got taken care of. There's chapter 8 optional problems, chapter 8 required problems, and chapter 8's exam will be available later this week after we do the last section. And it's labeled as Thermochemistry exams - Corona, because there's like another exam there that I want to make sure it doesn't pop up in front of you. So it is labeled with Corona. And then one of the conditions that I put into this so that you actually would practice is you must get a 75% on the required AL problems to be allowed to take the thermochemistry exam. So did not realize that was a criteria that I could do. It looks pretty interesting. I think that it's more than fair considering the scores that most people have gotten on the required problems. 75% seems really, really doable, and plus you have a number of opportunities to take it. And then on OneNote, I've given lots and lots and lots of videos. There's a lot of videos revolving around enthalpy and Hess's law and enthalpies of formation. So I probably put about almost a dozen, probably 8 to 12 different videos on there. Watch whichever ones you need to in order to understand. But we're going to go through my version of this, and then we'll do another opportunity with one more section. So this is chapter 8, thermochemistry. We're going to do, today's video is going to be involving what thermochemistry, what enthalpy is, and what are thermochemical equations, and both those involve stoichiometry and Hess's law. And then the video that I'll put together a little bit later on is going to be, the next video is going to be about the enthalpies of formation. We are not going to do bond enthalpy and first law of thermodynamics, although first law of thermodynamics is pretty straightforward, but we'll address those a little bit later on. Come to AP next year, and we'll get that. Okay, so section 3, which is the enthalpy section, talks about this concept of enthalpy. Enthalpy can best be described as stored chemical energy. It's a state property. It's kind of a concept of, like I said, that potential energy, but chemical energy, potential chemical energy. So if you think back to physics, when you were in physics, there was 2 types of energy. There was kinetic energy, and there was potential energy. Kinetic energy was the energy of motion. So you did a boatload of roller coaster type problems where you had the roller coaster at the top of a hill and had all potential energy, and at the bottom of the hill it would have all kinetic energy, and it would be the amount of kinetic energy was dependent on how high the hill was. So it turned the potential to do something because of the height into kinetic, the motion. Well, in chemistry, we kind of do the same thing, but we take the enthalpy, the stored energy, and turn it into some type of a observable energy, whether it be heat or light or work. But enthalpy is the amount of energy that is stored in the molecules. There's a couple great videos on enthalpy on OneNote that does a much better job than I am about explaining this, but the concept is, the best way to look at this is that it is an idea, a cop-out way of saying when a molecule or when a series of molecules react, they are going to release or they're going to absorb energy. They're either going to be exothermic or endothermic. Well, how does a material, say, I always use the example of a piece of wood. How does a piece of wood, when it burns, release energy? That piece of wood is not hot. That piece of wood does not have heat in it. Or does it? It actually has energy in it in the form of enthalpy that is ready to be released as heat. that stored energy that's in the bonds more than anything else. There's other places it is. There's vibrational energy, there's translational energy, there's all kinds of different energies involved in that wood, but enthalpy is a real easy overarching way to explain what that energy is. So it's stored energy. It is enthalpy. So we're not going to focus necessarily on the amount of enthalpy materials have. We're going to look at the amount of enthalpy change that takes place. So delta H, we use a symbol H. I don't know why. I'm assuming because it's kind of connected to heat. Delta H as being the symbol for change in enthalpy. You're going to take the enthalpy of the products minus the enthalpy of the reactants. Remember when we did delta for delta T, it was final minus initial. It's the same thing here. What's final in a chemical reaction is the products. What's initial is the reactants. So if we are going to look at how much heat is lost or gained in a chemical reaction, we're going to be looking at the amount of enthalpy that is changed, not enthalpy per se exact, enthalpy that is changed. So when we have delta H being negative, that's what it means when delta H is less than 0. That's going to be an exothermic process. Think about that. If the stored energy goes down, that means it lost some of that stored energy. It lost stored energy. It released it into the surroundings. That would be a negative change in enthalpy. A positive change in enthalpy would be endothermic. If the stored energy goes up, the energy coming into the system has to go up. So that would be a positive change in enthalpy. And it is a state variable. They talk about state functions and state variables, meaning it doesn't matter how it gets to that process, how it gets there. It's more a matter of the amount of change. The example that was given, I think there was one of the cool videos, was on the crash courses. They talk about a car that's on the top of a hill. If the car is on the top of the hill and it's going to come down and it's going to have some kinetic energy at the bottom of the hill, there's going to be an amount of energy that is going to be lost from the top of the hill to the bottom of the hill. However, that energy can dissipate or be released in multiple ways. If you go down the hill, but you have the brakes on the car, then the example they used was you're going to generate a whole lot of friction in your wheels, and therefore it's going to release a lot of heat. And at the bottom, it's going to have a tiny amount of kinetic energy because it's going to go down slower. Versus if you just let it go and it gets down to the bottom, boom, it's going to release it's going to be going really, really fast. So what's that energy become? Does that energy become heat and speed, or does that energy become just speed? But no matter what, the amount of energy that is released by the car from the top to the bottom is going to be the same. That means the energy released is a state variable. The amount of heat is not. The amount of kinetic energy is not. The amount of energy released is a state variable. So we're not worried about how that heat is released. We're just saying that it's going to release a certain amount of energy or enthalpy, and it will manifest itself in a bunch of different ways. For us, we focus a lot on reactions that release heat, so they warm up the surroundings. So we have a change, a negative from reactants have high to products have low. That's going to be a negative. Reactants are low, products are high. That's going to be positive. That's exothermic when it's negative, endothermic when it's positive. Okay, what about these equations? So there's a couple different things about equations, but we're going to focus on the way equations are presented. Normally it's just a chemical equation that also includes, in addition to the products and the reactants, like a typical balanced chemical equation, but it also has an appropriate value and sign for delta H. It tells you how much the change in enthalpy is of the reaction. So for instance, here's one. Ammonia is generated by the reaction between nitrogen gas and hydrogen gas. So nitrogen plus hydrogen gives you ammonia. We've seen this before. It's a pretty common reaction. Probably seen it all the way back in Chem 1 as a typical one that has weird coefficients of 1, a 3, and a 2. But here's the piece that makes it different. Over here, in addition to the balanced chemical equation, we are going to include a delta H. Notice the delta H is first negative. That means this reaction as written is an exothermic process. This reaction as written is an exothermic process. And second, there's an amount of energy. What that means is for every 1 mole, there's a 1 here in front of nitrogen, for every 1 mole of nitrogen that reacts with an excess of hydrogen creating 2 moles of ammonia, you're going to have 92.6 kilojoules of energy being released. Vice versa, if I take 3 moles of hydrogen and I react it with an excess of nitrogen, then I'm going to create 92.6 kilojoules of energy. These numbers out front, these mole numbers out front, are proportions, are ratios to the amount of energy that is a part of the thermochemical equation. This shows you how nitrogen and hydrogen are created together to make that ammonia that we were just talking about. Okay, and here's another one that shows you endothermic processes and the like. Okay, so what are some conventions? First off, you know that delta H indicates a sign, indicates the direction, whether it's exo or endo. Exos are negative, and endos are positive. The coefficients in the thermochemical equation, they represent the number of moles of the reactants or products. Phases matter, phases matter, phases matter. If you're looking at a reaction, one that has a liquid and one that has a gas, they're going to give different amounts of total energy. So basically making sure that the phases are specific. And the values of delta H when products or reactants are the same temperature, we're going to deal with in the next video. We'll talk about the numbered delta H's that are be tabulated for you, but we're going to do them as standard conditions, usually 25 degrees Celsius. Okay, so let's talk about some of the rules of thermochemistry. So first off, we mentioned that the coefficients out front have a significance. The coefficients out front have a significance. For every 1 mole of nitrogen that reacts with 3 moles of hydrogen, you're going to get 2 moles of ammonia, and when that happens, you're going to release 92.6 kilojoules of energy. Well, the magnitude, the number, the quantity is dependent on the amounts of the reactants or products. So if I had to think in terms of ratios, I'm going to release 92.6 kilojoules for every 1 mole of nitrogen, going to release 92.6 kilojoules for every 3 moles of hydrogen, or I'm going to release 92.6 kilojoules for every 2 moles. There's a relationship between the coefficients and the balanced chemical equation. So if I had to rewrite this equation for some reason, you'll see why a little bit later on, by tripling all my coefficients. So 3, 9, and 6. I've tripled all my coefficients. If I rewrite this equation, but I've tripled all my coefficients, that means I have to also triple the amount of heat. So instead of releasing 92.6, if I had 3 times as much of everything, I'm going to release 277.8 kilojoules of energy. I'm literally going to be increasing the amount of energy by a multiple of whatever I've multiplied all my coefficients by. Second is if I have this reaction, and again, 2 moles of hydrogen react with 1 mole of oxygen to give me 2 moles of water, that's going to release a whole lot of energy. But if I were to want to, and this is something that is done as a demonstration sometimes in Chem 1, if I were to break water into its components, I'm going to take water as my reactant and release hydrogen and oxygen in the process by something like it's called a electrolysis, where you add electricity and it separates the molecules. Then, if I'm going to flip the reaction, I'm going to write it backwards. Well, then my delta H is going to be quote unquote backwards. It is going to have the same amount of energy, but it is going to be opposite in sign. So if I start with water and make again, this is exactly the same reaction, just written backwards, then the amount of energy is going to be the same, but instead of it releasing that energy, I have to put that amount of energy in. So if I flip the reaction, I'm going to have the same exact amount of energy, but with the opposite sign. Kind of makes sense. If I'm going from A to B, it's going to be negative. If I'm going B to A, it's going to be positive. So we've got this same, A is the same spot, B is the same spot. The only difference, the amount of distance between the two is the same. The only difference is which direction you're going, and that indicates whether it's exothermic or endothermic. Okay, so third rule is the one that actually is sometimes referred to as Hess's law, and that's what we're talking about. We're going to deal with as our last piece. It says that if I have a reaction, or I even can write a reaction in such a way that it's represented as steps of various numbers, different reactions. Sorry, let's phrase that a little differently. If I were to rewrite a reaction as a series of steps, I'll show you one in the next example, where the steps add up to give my overall reaction. If I could algebraically show a reaction as the sum of multiple reactions, then as Hess's law says, then the heat of the overall reaction is the sum of the heats of the individual reactions. Nice graphical way to show this is if I want to know how much energy it takes to go from A to C, but I only know how much energy it takes to go from A to B and how much energy it takes to go from B to C, I can add up those two heats. I can add up delta H1 and delta H2 to get delta H overall, noticing that they just literally just add up to give the overall reaction. So let's look at an example. Suppose I look at a Bunsen that we use in our labs, and one of the main gases that are in there is methane. And thermochemical equation for methane is CH4 plus 2 H2O gives you carbon dioxide and water, and has a delta H of negative 890.3 kilojoules. What if I want to calculate what is the delta H going to be for reacting not a mole of methane, but I'm only going to react 5 grams of methane. What's that going to do? Well, this turns into being just simply stoichiometry using thermochemical rule number 1, where we're going to go from mass to mole like we did in chapter 3, and then we're going to go from mole to change in enthalpy overall using that ratio of 390 kilojoules per mole of methane. So we take our 5 grams divided by the molar mass to get moles, multiply times the negative 890.3 kilojoules per mole. Moles of methane cancel, grams of methane cancel, and I get that I release only 277 kilojoules of energy. 5 grams is less than 16 grams. 5 grams, I do not have a full mole, so I'm not going to release a full 890 kilojoules of energy. Okay, that's one application of the thermochemical equations. Here's some different delta H's for different phase changes and the like. We're going to deal with this in excruciating detail in the next video, talk about what happens with the amount of heat that's lost during the different vaporizations and fusions. We talked about that a little bit in the last chapter also, but we're going to focus a little bit more on how to use some of this tabulated information in the next video. So let's think about doing this. We want to know what's the energy that is released when 1 mole of water is broken into 1 mole of hydrogen and a half a mole of oxygen. I want to know how much energy is released or absorbed when this reaction takes place. Again, with the concept of having only 1 mole of water making 1 mole of hydrogen and a half a mole of oxygen. 1 mole of hydrogen and a half a mole of oxygen. So here's my reaction that I know information about. I can look this up in a table and I can see that hydrogen plus oxygen giving me water in my normal situation is going to release 571.6 kilojoules of energy. Well, if I think about it, I look at this and I see that instead of making 2 moles, I want to react only 1 mole. So first off, I had to flip the reaction because the water's on the wrong side. And then I've got the wrong coefficient out front. So I got to divide all my coefficients by 2. So what I'm going to do is I'm going to take my second law, knowing that I have to reverse the reaction, flip it, right? I have to put the water on the right side. And then I have to change my coefficients by dividing everything by half to give the right equation. So if I take my reaction and I flip it, okay? Now notice what I've done is this is that reaction. I flipped it to put the water on the correct side, on the reactant side. Then I know that this reaction, as written, has a positive 571.6 kilojoules of energy. I've reversed the sign. But again, I have the wrong coefficient out front, so I didn't want to have a 1 there. So now I have to divide everything by 2. So if I divide everything by 2 to get the right coefficient, that means I have to divide by 2 or multiply times 1/2 that value of 571.6 kilojoules of energy. This is the new amount of energy. This is the amount of energy, 285.8 kilojoules, is the amount of energy that is going to be absorbed when when 1 mole of water reacts with 1 mole of hydrogen to create a half a mole. God, I said that all wrong. Let's try this again. It's early in the morning, guys. When 1 mole of water breaks down to make 1 mole of hydrogen and a half a mole of oxygen, when that happens, it's going to require an absorption of 285.8 kilojoules of energy. So that's what happens if you have just one reaction. You want to flip it and divide through by whatever. Well, let's see how we can use this in a bigger sense. Suppose I know this. I know these reactions, and this is very, very typical a way that Hess's law is laid out. This is they'll give you 1, 2, 3, 4, 8 reactions, and they'll know how much delta H there is for each one of these reactions. And then they'll say, well, figure out how to calculate the amount of heat that's lost by another reaction that's not one of those. And you have to, this is where it's kind of like playing with a puzzle. The numbers all have to link together just right. You're going to have to manipulate these reactions in order to make them add up to give you this overall reaction. So let's try this one. So I want to make this reaction up top. Okay, I'm going to move my little timer. I want to make this reaction that's up top. I want to find out how much heat's involved in this reaction that's up top. And I know these two reactions. So first thing I do is I start looking at the reaction that I'm going with. And I notice a couple things. One, I notice that carbon is on the reactant side. And in one of my reactions, carbon is, and only one of my reactions, carbon is also on the reactant side. So in order to, there's no carbon by itself in the second reaction. So if I just take that first reaction and I rewrite it, then I know that my carbon that's in my final reaction is in the correct place and it has the right coefficient. So I don't have to do anything with that first reaction. Okay, what about the rest? Well, second, I notice this oxygen is all over the place. I do not want to deal with that. I'm going to be totally honest. If you have an element that is in multiple locations, do that one last, or just hope that everything adds up nicely so that they cancel themselves out. So I'm going to skip over the oxygen. Then I'm going to look at my carbon monoxide. Well, carbon monoxide is in the second reaction, but we have problems. First off, it's not on the correct side. Okay, in the desired product, it's on the product side. In the reaction that's given to me, it's on the reactant side. So I know first and foremost, much like our last example, I'm going to have to flip the reaction. Second, it's got the wrong coefficient. So not only is it on the wrong side, it's got the wrong coefficient. So I'm going to have to flip this reaction and divide everything by 2. So look what I did. I flipped the reaction. Now my carbon dioxide's on this side, on the reactant side, my carbon monoxide's on the product side, and my oxygen's on the product side. And I took all my coefficients and divided them by 2, which means for this reaction with the release of 566 kilojoules of energy, I have to flip it. So I'm going to change the sign to be positive, and then I have to divide it by 2. So it becomes 283 kilojoules of energy. And then, since I know that I think these add up, let's see. If I try to add them up, my carbon dioxide's balance, they cancel each other out. And then my oxygens, on this side I have a whole oxygen, but on this side I have a half. So if they balance each other out, I'm going to get that half on my reactant side. So they all add up to give me the overall reaction. So if they add up, these two reactions add up to give me my reaction I want, then my heats add up to give me my amount of heat that I want. So this reaction will release 110.5 kilojoules of energy. Okay, it's a puzzle. You want to make sure everything balances out, everything adds up nicely, everything cancels out. If it doesn't, you did something wrong. It's kind of has a really great satisfaction of being able to test yourself to see whether you did it right. Let's look at one more. So I want to take this, I want to figure out how much heat is needed or how much heat is released or absorbed when this reaction takes place, given these 3 reactions. Oh my goodness, 3 reactions. So I have 3 reactions with known amounts of heat. I want to see how they might add up to give me my reaction that I'm shooting for. So again, same logic. I walk my way across. from one to the other, and I make sure that my coefficients are in the correct side, my components are on the correct side, and they have the right coefficient. So I look for my carbon. It has 3 carbons in my desired reaction, but in my reaction that I was given, the only one of the reactions has carbon by itself, and that carbon is on the right side, but it has the wrong coefficient. So I'm going to have to take this reaction and rewrite it, but multiplying everything by 3 to get the 3 out front. So I'll multiply everything by 3. Then I have to triple my heat that was there. So the negative 393.5 times 3 is negative 1180.5. Okay, next component, hydrogen. I have 4 hydrogens in my desired reaction, but I only have 2 hydrogens in the only reaction that has just hydrogen in the examples. So, but it's on the correct side, which is awesome, but it has the wrong coefficient. I want a 4, it has a 2. So that means for this third reaction, I have to multiply it by 2 to make sure there's a 4 out front. So if I multiply everything, all my coefficients by 2, then I have to double or multiply times 2 my amount of heat from that reaction. And then finally, last one, I'm going to look at my propane, C3H8. My propane is going to, I notice that it's here in this third reaction that I was given, the very, very first one, but it's on the wrong side. It's got the right coefficient, but it's on the wrong side. So what I need to do is flip it. So if I flip it, when I flip the reaction, notice I put the propane and the oxygen now are on the product side, and the carbon dioxide and the water are on the reactant side, and they all have the same coefficients they do in the original reaction. All I have to do is flip the sign, so it goes from a negative 2043 to a positive 2043. Then I want to see whether they add up. So let's see. Cancel out my carbon dioxides, cancel out my waters, cancel out my oxygens. There's 5 on that side, 3 plus 2 is 5, and there's 5 over there, so they cancel. That means I'm left with 3 carbons, 4 hydrogens, and a propane, so that does add up. So if I add these heats up, I get that it requires an absorption of 1,852 kilojoules of energy to make this reaction take place. It's going to be an endothermic process. Okay, one last example. Okay, try this one on your own. Go ahead and hit the pause button. Try this one on your own. It's a little trickier, but try this one on your own, and I'll be back in a minute to go over how to do this problem. Hit the pause button. Did you hit the pause button? Did you try? Did it go well? Did everything add up right? Let's see how it works. So, this is the reaction I'm shooting for. A lot of N's and O's. Here's the 3 reactions I have. So, first thing I'm going to do is I'm going to check my N2O, and I notice that the N2O is in the third reaction and only in the third reaction, but it's on the correct side. Awesome, but it has the wrong coefficient. So I need to divide this third reaction by 2 to make sure that there's only a 1 out in front of the N2O. So I'm going to divide all my coefficients by 2, and therefore I have to also divide my delta H by 2. Then I'm going to look at my next reaction, next component, NO2. NO2 is in only one reaction. It's on the wrong side, and it has the wrong coefficient. So I'm going to have to flip the reaction, and I'm going to have to multiply everything by 1/2 or divide everything by 2. Same idea. NO2, flip it to the other side, NO to the product side, O2 to the product side, and divide everything by 2. Therefore, I have to flip the sign, goes from a negative to a positive, and I have to divide the number by 2, 56.6 kilojoules of energy. Then the last one's where it gets a little tricky. NO is in the only one reaction, but it's not. It's in 2 reactions. It's also in one of the reactions I've already used. So I need 3. I already have 1 in the reactions that I've used already. Therefore, I need 2 more. So I can just take this second reaction and write it straight up directly as written. It's on the correct side. It's on the product side, which is where I want it. That's where that one is too. So I'm just going to rewrite that reaction. And then let's see whether they add up. So let's see, get rid of my nitrogens, get rid of my oxygens, and notice what I have left over. N2O, NO2, N2 plus 1, 3 NOs. So it all adds up nicely. Therefore, if these reactions add up to give me my overall reaction, then these heats will add up to give me the overall heat. It absorbs 157.6 kilojoules of energy. Okay, so that's Hess's law. Pretty satisfying. If you want, what I'm going to do is I'm also going to put some extra Hess's law problems onto the onto OneNote for you to practice if that doesn't work for you. But I'm also going to put a link in OneNote to a place where you can actually do a lot of them just until you get the hang of this. They're kind of satisfying because they're very puzzly. So what's next? Well, what's next is the last section of this chapter. Is going to be all about enthalpies of formation. The next video should be significantly shorter because the next video uses one concept and is pretty quick, down and dirty. But it's a very common concept that we're going to use throughout Chem 2 and AP. You guys be safe, be healthy, practice your social distancing, and I will see you in the next video. Always remember, never forget, sig figs do matter. See ya. Toodles.